Hello, this is an introduction, not an introduction, a complete review for all the material in AP Stats. And so, a quick intro. So, these lectures are primarily just for the intended purposes tips. So, solving problems quickly, the concepts, and try to focus more on intuition rather than memorization. And so, before um, before starting the lecture, you should already know the content. This is just a deep dive into the content, if you will. So the book that I'm using as reference is the Barron's 7th edition. The Barron's 7th edition AP Stats. So that's the book for reference. And this is the most important question I have to tell you is, when do you take notes? So I would suggest not taking notes during the lecture, but rather after solving the problems, and just after the lecture, because you can't really take notes during the lecture, and you'll miss out on some of the important stuff that's said. So pay attention during the lecture and then take notes after. Yeah, that's it. Okay, so let's start with the first chapter. So this is chapter 1, which is graphical displays. And there are two types of variables that you need to know about. So one is categorical, and one is quantitative over here. So an easy way to make sense of what is categorical and what's quantitative is to look here at the x-axis. So for example, here we have types of pi, right? And in a categorical variable, you can't take an average. So you can't average the type of pi, right? It's definitively separated into one category. But in quantitative, say we have goals per person, you can't do that. You can't take an average. You can find out the average goals per season, right? So that's the biggest difference. And as long as you know that, you can yeah, that's all you need to know. So for categorical, there's three main ways of representing the data. You have bar charts, you have pie charts, and you also have dot plots. And so these bar charts are the most important. Then you have pie charts, and then you have dot plots, right? Okay, so let's start with a very important concept for not only categorical and quantitative, but generally throughout, which is this idea of frequency. So what is frequency, right? And if we look over here at this graphic that I made, I can zoom in. Okay, there. So frequency is really the exact number. That keyword is important there. Exact. The exact number of times that something was measured. So if we look at this bar chart on the left, for types of pie, specifically apple, 10,000 people said they like apple pie the most. The graphic is a bad one, I admit, but it was just to show the point of frequency. So yeah, so frequency is the exact number. But if we look here to the right, you have something called relative frequency, which is got by taking the frequency. So say 10,000 people like apple, right? So the relative frequency for apple is just 10,000 divided by the total number of people, right? So that would be 8k plus 10k plus 5k, and that would give you this 43%, right? So the most important concept here is really just about heights. So usually you're not given the frequency, but rather you're given relative frequency, right? And the most important thing you can observe about relative frequency is the correlation with height. Note that when I've converted this graph over here on the left to the graph on the right, the height of the bars stays the same. I've just changed the numbering. Here it's frequency and here it's relative frequency, right? But what do you notice about this graph over here? Well, you notice that, first of all, the y-axis, it sums up to exactly 1, because you have to encompass 100% of your data, right? So the y-axis must add to 1. And then you also notice that the the apple bar is a little bit taller, which tells you that there is more people chose apple, right? So that's frequency and relative frequency. And you need to understand that height in a bar chart represents relative frequency if the data is given in percent. If it's not given in percent, then it just represents frequency. So, oops, the number one big point is, oops. So the number one big point is, what is frequency versus relative frequency. And if you can understand this, the rest of the chapter becomes easier. Okay, so that's everything about categorical variables. Now moving on to quantitative, which is far more interesting. And of course, the most important thing in quantitative is the histogram. So I'm sure all of you have seen histograms before, but what I really want to do here is tell you all about the sort of interesting stuff they can do with this histogram, so to confuse you, right? So let's start with the one on the top left. Now this notice again, relative frequency. So it's always important whenever you analyze a histogram, you look at the x and the y-axis, specifically this relative frequency, and also where exactly the numbers are. So you see that you have a number here on the left interval, and then a number here on the right interval, right? So it's crucial to understand what is this telling you. This is simply telling you that between 0 and 1, I have 43% of my data, right? But now, so this is the first important point. And the second important point is over in this graph. So say I want to transform this graph over here. So say I want to transform relative frequency into frequency, and I'm given this graph here with the intervals. Can I do it? And I think you should think about this. Can you do this? And the answer obviously is no, you cannot do this, right? Because like we said here, you need to have exact categories. Okay, we've switched to variables, but this is an interval. It's telling you between two values how much percent of your data falls in there, right? But if you were to get a frequency exactly, what would you say this x value is? Say you have 3 x values, right? What would you say this value is? Well, you don't know. All you know is what happens in the interval, but you don't know what happens at each individual x value, right? So you can't do this. That's the second most important point. You can't do this. But this is the third one. What if your histogram was like this? So I'm going to pause and think about this for a second. What if it was like this? Right? Because if it is like this, well then you know exactly what the frequency is. Actually, let's go from this diagram here. Now you know exactly what your x-axis is. It's just each individual value, 1, 2, and 3. And now you can indeed go from the relative frequency to the frequency, and it'll make sense. And if you know that this graph, these two, you can see how the height of the histogram hasn't changed, just the values. But that's only because each of these values belongs to one bar, right? But over here, each of these bars belong to an interval. So all you can really do is take relative frequencies. But here, in this rare case that you are given a bar for each value, you can get both the frequency and the relative frequency, right? But most of the time you'll be dealing with this one over here. So that's the only part you need to know. And apart from that, you just need to know that relative frequencies mean area, just like we've established here, that all of the data sums up to 1 because you have 100% of the data. So relative frequencies mean relative areas. Okay. Let's see. is there anything else? Okay, so let's talk about binning, center of histogram, and we've already done area, so we don't need to worry about that. But let's go to binning. What does binning mean? Well, binning just means that the width of each interval is uniform, right? Because say it wasn't uniform. Say it was, say it wasn't uniform, and say this was, say this was 4, and that was 12, and that was 19, right? Now the problem with this type of binning is that you can't tell, you can't make any judgments about the data because you don't know anything much. You only know that, in other words, it's misleading. This graph is misleading, right? Because, what conclusion will you make here? The intervals are different. So, is this bar, the question really is that if I was to split this into uniform intervals, this graph would change, right? So you can't make any conclusions based on non-uniform intervals. So you've always got to have uniform width. Okay, and it's center of an histogram is always which line, if you think about it, which line will divide the histogram into exactly 50% area on either side. So let's look at this one, for example. They're all the same, but so we see that most of the data falls in here, and then if I divide this into, so I would say that the line is, so the middle of the histogram, I would say, is somewhere over here, right? Because this part has 50% of the data, and that part has 50% of the data. And this is also called the median of the, yeah. So the center of a histogram median, okay, and it cuts the area into 50% on either side, okay? Okay, there's histograms. Now we'll talk about shapes. Yeah, okay, so the only 4 major primary shapes you need to concern yourself with is this one, that one. So this one is called right skewed, and the reason it's right skewed is because most of the data falls on the left, right? And usually there's this odd data point here that doesn't belong here that is skewing the entire distribution to the right. And similarly, over on left skew, so this is left skew, oops, you have most of the data falling on the right, but you have this odd data point over here that's skewing everything to the left, okay? And then we also need to talk about symmetrical and bell-shaped. So this confused me at first because I thought they were the same, but they're not. Symmetrical means if I cut this into half, will the halves be mirror images of each other, right? But the bell-shaped distribution is a very specific symmetric distribution, as in it only has one mound, they call it. But what it really means is that most of the data is concentrated within, you only have one big lump. And then you have 2 equal tails. So these things are called tails. So you have 2 equally sloping tails, and then you have a center, right? And you can see that this is clearly not that. So bell-shaped distributions are symmetrical, but not all symmetrical distributions are bell-shaped. That is point number 4, very important. Yep. Let's see. Oh, shape. Okay. So for shape of distributions, you really need to understand Okay, for shape of distributions, it's in the book. It's called SOX. I'll quickly tell you everything you can possibly say for SOX. Actually, give me a second. Okay, so here I have it. So for shape, okay, for shape, you can talk about, for the case of chapter 1, you talk about skewness, you talk about if it's bell-shaped or symmetrical. So that's all you have for shape. And then you can also talk about the modes. So remember how here I said that this one only has one mound, so one place where the data is gathered mostly. But look at this one. It has, well, definitely more than one, right? So you talk about that. Does it have one mode, two mode, which the terminology for these is unimodal and bimodal, right? So you talk about that. Then you talk about if it has any gaps, clusters, things like that. So gaps and clusters mean, say I have a distribution like, say I have a distribution like this. Now this part is a gap. There's nothing here, right? And in fact, if I look at another distribution, say I make a scatter plot instead now. I would say that there's two clusters. Most of the data is clustered here and here. There's two clusters that I can cluster the entire distribution into, right? So that's and then you have clusters and gaps. Okay, cool. So now you want to talk about outliers, and outliers are more dived into in the next chapter, chapter 3. So for now, all you need to know is that an outlier, especially here, let's look at these distribution. So these points I was talking about that feel out of place and skew the entire distribution, these are called outliers, potential outliers. So every time you have skewness, you should always indicate that there may be potential outliers, right? Center, right? So right now we've only looked at the histogram for center, in which case the center is usually the median, which cuts the data into 50%. And then lastly you have spread, okay? And spread is just, for chapter 1, it's the range, so the maximum value minus the minimum value, okay? And tip number 5 here. Your answer is useless without values. So if you have the values, give them. It just makes concrete evidence that what you're saying isn't completely nonsense, right? So every time you have values, give them. Yes, that is it. Oh yes, and you also have stem plots. So why would you use a stem plot? Well, you would use a stem plot if you wanted the individual data points. Once again, in this interval, you don't get that. You only get the intervals. With a stem plot, you have the actual data, and you can make a histogram, but you also have the actual values, right? Okay, and another very important thing about histograms is this fact. So the right, if we look at this one, the value 0 is included, but the value 1 isn't included, okay? So this is included, but this is not included for the interval 0 to 1, okay? And for the interval 1 to 2, 1 will be included, but 2 isn't included, okay? And for the last interval, both 2 and 3 will be included, because again, you have to have 100% of your data, right? You have to include everything that's left. That's about it. And the last thing here is ogives, which I saved for last because they are the hardest. Okay. So what an ogive really is the word, it's called a, already did this. Okay. Ogive is called a cumulative frequency distribution. Okay. So what does that mean? Well, we know what frequency is, and we also know what relative frequency is. And we know that all the relative frequencies must add to 1, right? And a histogram, an ogive is simply graphing that. So what it's telling you is, okay, say you have a normal distribution. So I mean, distribution, say you have a bell-shaped distribution, right? Okay, now if I asked you to make an ogive of this, what you would do is, you're basically, the question really is, as, say you're just a tiny point over here, you're starting at the start of the distribution, you're a point over here, right? The question you're going to ask yourself is, as I move along the x-axis, right, how quickly does the area behind me increase? Okay, so let's take a look at what that means. So as you're going here, first you have very small amount of data, and then you're going here, now you suddenly have a little bit more data, and the data that you had before and now, well, you got this data really quickly, right? And then as you go to the middle, you find that only within this short time span, you've got all this new data, a lot more of it. So how would you describe this? Well, you would say that first, I didn't get a lot of data, then I started getting a lot of data, and then at some point, I stopped getting data, which would be this middle point here, and then, well, then I wasn't exactly getting so much data, so I stopped. I was getting data, but not so much, and finally over here, I stopped getting data. That's the question that really is, and just supposed to end this video, I'll just leave you with the question, given this ogive, what is its distribution? Okay, and oops. So that's the last question. And again, the best way to interpret an ogive is its slope. So you want to look at how fast am I getting data. Here, we got slowly, and then we moved on. We got it really quickly, and then it kind of plateaued at this point, and then we started getting data more slowly. But what about here? Yeah, so based on this slope, specifically a big hint is this line over here. It's very vertical, so what does that tell you? And that's a question for you. So with that, we are done this video. Do all the questions for chapter 1 and then take notes. Yep, see you in chapter 2.